Hello everyone, my name is Jyoti and today we'll be discussing Diffie-Hellman key exchange. So, first of all, we'll see what all points we need to cover under Diffie-Hellman key exchange. We'll be seeing introduction, algorithm, implementation, example, application, and the last is conclusion. Diffie-Hellman key exchange involves a simple public key algorithm. In public key encryption, schemes are secure only if authenticity of the public key is assured. The protocol enables two users to establish a secret key using a public key scheme based on discrete algorithm. So what happens? Let's take an example. Let's suppose two users are there, Alice and Bob. They want to share a secret key among themselves so that only they can encrypt the message. In that case, Diffie-Hellman key exchange method is used. The protocol is secure only if the authenticity of the two participants can be established. The purpose of the algorithm is to enable two users to securely exchange a key that can then be used for subsequent symmetric encryption of messages. The algorithm itself is limited to the exchange of secret values. The Diffie-Hellman algorithm depends for its effectiveness on the difficulty of computing discrete logarithms. Let's see Diffie-Hellman key agreement protocol. First one is exponential key agreement. Second, allows two users to exchange a secret key among themselves. Third, requires no prior secrets. And fourth one is real time over an untrusted network. Let's get started with algorithm. So, Diffie-Hellman key exchange algorithm involves global public elements. They are Q, which is a prime number, alpha, which is primitive root of Q, and alpha is less than Q. How user A key generation takes place. Select a private key XA and that XA should be less than Q. Now, the public key of A can be generated as YA is equal to alpha power XA mod Q. In the same way, user B key generation involves a private key which is selected as XB and XB should be less than Q. The calculation of public key of user B is as XA par XB mod Q. Calculation of secret key by A involves K is equal to YB par XA mod Q. Calculation of secret key by B involves K is equal to YA power XB mod Q. Let's see what is under implementation. In this scheme, there are two publicly known numbers, a prime number Q and an integer alpha that is a primitive root of Q. If you all don't know what is primitive root, then please note this point. Primitive root of a prime number P is one whose parse module P generate all the images from 1 to P minus 1. I'll be elaborating primitive root in a more deeper manner further. In this, it is shown that user A selects a random integer XA which is less than Q and computes YA is equal to alpha power XA mod Q. Similarly, user B independently selects a random integer XP which is less than Q and computes YB is equal to alpha power XP mod Q. Each side keeps the X value private and makes the Y value available publicly to the other side. Thus, XA is A's private key and YA is A's corresponding public key. And similarly for B. User A computes the key as K is equal to YB power XA mod Q and user B computes the key as K is equal to YA power XP mod Q.
Before solving Diffie-Hellman example, it's necessary to know what is primitive root. So, primitive root is explained as for any prime number p, if we have a number a such that powers of a mod p generate all the numbers between 1 to p minus 1, then a is called a primitive root of p. In terms of the group terminology, A is the generator element of the multiplicative group of the finite field formed by mod P. Then, for any integer b and a primitive root A of prime number p, we can find a unique exponent I such that b is equal to a power I mod p. Let's take an example of primitive root. First one is a mod 7. So we need to find out the primitive root of 7. Form a table and write column wise 1, 2, 3, 4, 5, 6. As we need to take the numbers from 1 to p minus 1. And here p is equal to 7. So 7 minus 1, that is 6. So column wise we have written 1, 2, 3, 4, 5 and 6. Now, row wise, we need to write a power 1, a power 2, a power 3, a power 4, a power 5 and a power 6 along with mod 7. So, calculate for all. Here a is equal to 1, 2, 3, 4, 5, 6. After calculation, we'll be able to see that unique elements are seen in row 3 and row 5. Hence, 3, 5 is the primitive root of 7. After knowing how to calculate primitive roots, let's see the example of Diffie-Hellman key exchange. Consider Q is equal to 353, alpha is equal to 3. 3 is primitive root of 353. A and B discrete private keys, where XA is equal to 97 and XB is equal to 223. Each computes its public key. A computes YA is equal to 3 power 97 mod 353, which is equal to 40, whereas B computes YB is equal to 3 power 233 mod 353 is equal to 240. After exchange of public keys, each can compute the common secret key. A computes K is equal to YB power XA mod 353, which is equal to 248 power 97 mod 353, which gives the answer 160. In the same way, user B computes K is equal to YA power XB mod 353, which is 40 power 253 mod 353, which is equal to 160. Hence, we can see that after computation, key A and key B are same, that is 160. Application. The Diffie-Hellman protocol has been applied to many security protocols, including the security socket layer, secure shell, and IPsec. Secure socket layer or SSL. The SSL is the standard security technology developed by Netscape in 1994 to establish an encrypted link between a web server and a browser. This link ensures privacy and integrity of all data passed between the web server and browsers. SSL is used by millions of websites in the protection of their online transactions with their customers. Second, Secure Shell or SSH. SSH is a network security protocol very common for secure remote login on the internet. The secure shell has come to replace the unsecured telnet on the network and FTP on the system, mostly because both telnet and FTP do not encrypt data and instead send them in plain text. SSH, on the other hand, can automatically encrypt, authenticate, and compress transmitted data. Third, IP security or IPsec. IPsec or IP security is an extension of the Internet Protocol. It is a suite of protocols introduced by the Internet Engineering Task Force IETF to aid in configuring a communication channel between multiple machines. Let's see what is man-in-the-middle attack. A man-in-the-middle attack is a type of cyber attack where a malicious actor inserts him or herself into a conversation between two parties, impersonates both parties, and gains access to information that the two parties were trying to send to each other. A man-in-the-middle attack allows a malicious actor to intercept, send, and receive data meant for someone else, or not meant to be sent at all, without either outside party knowing until it is too late. Hence, man-in-the-middle attack can be prevented with Diffie-Hellman key exchange. Conclusion. The Diffie-Hellman key exchange exploits mathematical properties to produce a common computational result between two or more parties wishing to exchange information, without any of them providing all the necessary variables. By agreeing on two variables and providing each other with a computed public key, the resultant secret key will be identical throughout the exchange. It is of course possible to intervene by either masquerading or by sheer brute force, but the first is a common concern, authentication, which must be addressed separately, and the second is, when done right, computationally infeasible. With proper authentication mechanisms, proper prime generation, and true randomness in picking variables, the TH protocol can be a powerful component in many a security measure. Good implementations include usage in secure socket layers, secure shells, IP security, and others. Passages on short introductory and background information description issues as well as common usages were produced in this section, and it is hoped that they were all of sufficient clarity. Thank you so much.